Our first speaker today is Professor Tony Bloch from Michigan University, and the title of his talk is Dissipative Dynamics in Hamiltonian Non-Holonomic System. Thank you, Tony.
Thank you very much. Well, it's certainly a pleasure to be here. It's nice to be in Rio again. It's very nice to be celebrating Jair's birthday. And what I want to talk about today is certainly related to work that Jair has done. So I want to talk about some of the inspiration I got from his work on non-holonomic systems. But I also want to talk more generally about the kind of dynamics that one gets in non-holonomic systems. And then one saw a little bit of yesterday, for example, in Luis and Paula's talk about how in non-holonomic systems one doesn't necessarily get Hamiltonian-type behavior, but one gets dissipative dynamics in certain situations. And the sort of goal of the talk today is to talk about this kind of dissipative dynamics that arises in various contexts. In particular, I want to start off by looking at some of the work that I've done on integrable gradient flows, some of it with Tudor Rachu, who's here, and Herman Flaschke. And this is related to flows on the total lattice, which again is related a little bit to non-holonomic systems. Then I want to talk about its relationship in particular with certain kinds of non-holonomic systems of the sort you saw discussed yesterday. And finally, to generalize this to nonlinear non-holonomic systems. And by that I mean non-holonomic systems with nonlinear constraints, which give rise to a different kind of dissipative dynamics. And finally, I'd like to link these all together to show how in the non-holonomic setting with nonlinear constraints, one also gets double bracket type flows, which are related to the integrable gradient flows that I'll begin by talking about. So let me begin by talking about the total lattice, which I know is well known to many of you here. So this is a beautiful integrable system, a prototypical system, if you like, that's typical of integrable systems which are non-compact, in the sense that one gets dynamics on the line or series of lines rather than on a torus. So the system that I want to look at is this non-periodic finite total lattice following the treatment due to Jürgen Moser. And basically what it consists of is a set of n particles moving freely on the x-axis and interacting under an exponential potential. And a little later in the talk, I'll relate it to particles which are also on the line or in n space, but interacting under a non-holonomic constraint. In this case, it is perfectly Hamiltonian. You have the position of the kth particle denoted by xk. Yk is the velocity of the particle. And there is a potential term, which is the exponential of the difference between the two particles. You use the canonical Hamiltonian structure, and these are the Hamiltonian equations that you get. And the convention, which was introduced by Moser, I believe, is that e to the x0 minus x1, e to the xn minus xn plus 1 equals 0, which really corresponds to pushing the first particle off to minus infinity, if you like, and the last particle off to plus infinity. So it's sort of on the line, but in some sense finite. So that's a very convenient setting for analyzing this system. And it has a wonderfully rich structure that's been discussed by many people. In particular, one way to look at it is to make this transformation due to Flaschke and also to Manikov, the change of variables that I've written over here into the variables ak and bk. And in these new variables, the equations of motion become this set over here, which doesn't look that exciting, but the main point is that once you have it in this form, you can rewrite it in a lattice pair representation. And this is, many of you, of course, know, is what one really wants to analyze integrable systems. And in this case, the matrices take a particularly nice form. They're tridiagonal Jacobi matrices. L is the symmetric matrix with B's on the diagonal. And B is this matrix with A's on the off diagonal. And that's a common convention, although I know Carlos Tomei, for example, and Percy Deift use the opposite convention for the A's and B's. But in any case, that's the way we normally write it. And so you can show that this leads to an isospectral deformation. If O of t is the orthogonal matrix solving this equation, dd buddy O equals BO, where O is the identity, you can check that there's an isospectral flow. The eigenvalues of the matrix L are conserved. And in fact, for this system, this is enough to prove integrability, because the system is basically on a 2n minus 2 dimensional phase space. This gives you n minus 1 independent integrals. and it's enough to show integrability. You can show these integrals are both independent and commute under the natural Poisson structure. But there is more structure to this example. For example, if n is the matrix diagonal 1, 2, 3, and so on through up to n, you can show that the total matrix may be written in this double bracket form, L dot equals L bracket n. And that's not too hard to see. You can check that L bracket n is just equal to the matrix minus B, and it gives you back the original isospectral form. But the important thing about this is this turns out to be a gradient flow. In fact, it's the gradient flow of trace Ln. I'll come back to this in a second. And this goes back to the topological work originally done by Teicht and Tomei. But here you can show that there's an explicit metric called the normal metric and an explicit function, trace Ln, which gives rise to this gradient type flow. You can show, in fact, that this double bracket equation, restricted to a level set of its integrals, is the gradient flow of the function trace Ln with respect to the so-called normal metric. So I'm not going to say too much about this metric now, but it's a natural metric that exists on co-adjoint orbits. And it gives rise, in fact, to this flow. So there are several metrics that you can write down, including the Koiller metric, but this turns out to be the right metric for the flow. So from this observation, you can show a number of nice things that were known, for example, to Symes and Moser also in some sense, that the flow tends asymptotically to a diagonal matrix with the eigenvalues of L over 0 on the diagonal. And, of course, it has to be, since it's isospectral, once it flows to a diagonal matrix, the eigenvalues have to appear on the diagonal. And moreover, they're ordered according to magnitude. In fact, the ordering really is dependent on this matrix N. So if you can choose, in fact, this matrix N so as to order the eigenvalues in any particular way you like for an arbitrary double bracket flow, but for the total flow, you want them in this order, 1, 2, 3, and so on through to N. So you can do many nice things with this gradient flow. You can use it to order eigenvalues, if you like, find the eigenvalues. And in fact, the observation due to Symes is that the time one map of this flow is equivalent to the QR algorithm. So there's a nice connection with numerical analysis here. And there's been a lot of work on different kinds of double bracket flows recently. For example, with Tudor and Phil Morrison, we've looked at analogous flows on the loop group, which turns out to be nice. Darrell Home and Francois Gallmars have looked at other double bracket type flows. So that this turns out to be very nice both in finite dimensions and infinite dimensions. It gives rise to a beautiful series of different flows that you can look at that are this type and generally gradient-like. But the nice thing about this is it's both gradient and Hamiltonian. It's got this dual character, and you can think of it in some sense because you've extended this flow to infinity, but also because you're flowing on a level set of the integrals. So it's gradient on a level set of the integrals, and thus it's able to have this dual character, which is sort of rather rare, of course. Also, the nice thing about it is that the tridiagonal aperiodic total flow can be solved explicitly, and the way to do that is by a Gram-Schmidt process, which, of course, is related to QR. So the way you do it is you take the initial data, you factorize it into an orthogonal piece and an upper triangular piece, and the explicit solution of the total flow is just given by conjugation with this orthogonal piece. And here is just a simulation of the toda in 4 dimensions. So the Hamiltonian looks like that, and one has the equations of motion. In this particular case, it looks like this, and they conserve the trace, so there are these 4 equations. And you can check that the flow decreases along the orbit. Sorry, that's a little hard to see that, but you can see the eigenvalues sort of, you can see that if you just follow for example, the diagonal entries, you can see that they tend to the diagonal entries. So let me just mention another sort of related problem, which I've worked on recently with Tudor and Francois Gallmars. So one can also ask the question, if you just take a general solvable Lie group or a general total orbit, are these the only interesting integrable systems? Well, it turns out, of course, that it is a co-adjoint orbit, so you can write down, in fact, if you like, any nice Hamiltonian on the orbit and see what you get. In particular, it turns out to be nice to write down the rigid body Hamiltonians. So instead of looking at the rigid body equation, for example, on SO3, which one normally does, or compact Lie groups, it's nice to look at it on solvable Lie groups. And this is a fun system to look at. In this case, in the 3x3 case, the Hamiltonian looks like this. and you get this set of equations, which is just the Toda equations with a general rigid body type Hamiltonian on that orbit. And it also, in fact, gives rise to nice asymptotic dynamics, just like the ones that I showed you, although the eigenvalues are not necessarily preserved along the flow. In fact, it's not isospectral in the same way. And just to show you the generalization of this, as I said, there are many interesting generalizations of these flows. In particular, you can extend this to basically any lower Borel subalgebra, any reasonable algebra that you'd like, as opposed to just SLN. And what you can do is you can write down the rigid body Hamiltonian, as I mentioned, on this orbit in this very general way. This is this famous sort of Markov operator. So phi A, B, D is just the general inertia matrix for a system like this. So you write down a general inertia matrix, which looks like that. And you can write down the general flow with a Hamiltonian like this on a general Lie algebra. And this is what it looks like. So if you consider the Jacobi orbit, just the tridiagonal matrices, if you like, in this general Lie algebra, one gets a generalization of this of the Hamiltonian for Toda, which is just trace L squared, and the Hamiltonian looks like that. This is the operator which gives you the inertia tensor, and if you choose all these parameters to be trivial, basically A equals B and dji equals delta ji, one recovers the Toda flow. So to show you what the Hamiltonians look like in this general setting, so you can compute the Lie-Poisson equations. They look like this. So this is just the Lie-Poisson equations, which you saw a couple of times yesterday, but just on a general adjoint orbit. And the Hamiltonian equations look like this. And you can also do the Flaschke transformation to get you back from the adjoint orbit to T star Rn. And this is what the Hamiltonian looks like in the Flaschke type variables. And this is part of a larger project that I've been working on with Tudor, which looks at this general transformation. So the transformation from the adjoint variables to the canonical variables turns out to be generalizable in very nice ways. And in particular, you can see it here, but you can generalize it to many other systems as well. So that's sort of an ongoing thing of interest. Okay, so that's Toda, which is my archetypal dissipative type system. What I want to do now is compare it with some other systems which exhibit dissipation, in particular non-holonomic systems. But I want to start off with something a little bit related. So this is Toda you just saw is a Hamiltonian system which exhibits some kind of dissipation. It turns out that there's another way you can get dissipation in a Hamiltonian system, which is by extending things to infinite dimensions. So this relates, in fact, to work I did a long time ago with Jerry Marsden on dissipation-induced stabilities, where you have a damping in a Hamiltonian system, and the damping can sometimes give rise to stability, but it sometimes can give rise to instability, depending on the signature of the energy, in fact. But this can be so you can wonder if you could model that in a Hamiltonian way, and in fact you can do that if you extend things to infinite dimensions. And the simplest way of seeing it is this rather wonderful Lam model, which goes back to some work of Lam in 1905. This was a precursor to quantum mechanics. So what the simple Lam model is, it's an oscillator physically coupled to a string, and the vibrations of the oscillator transmit waves to the string, which are carried off to infinity. And that's an infinite dimensional system, but if you look at the oscillator by itself in isolation, that really just it looks like it behaves like an oscillator with damping. So let me show you briefly how that works. So the Lam model is very simple. It's linear. Here is Wxt, the displacement of the string with a certain mass density. And I just have a singular mass at one end of the wire, if you like, or the string. So we couple the string to the oscillator. So it looks like that. And so basically I have a wave equation. The dynamics of the oscillator, you can make it more complicated if you like, and it's just connected like this. So Q of t is equal to W0 of t at one end, and the force, the way that the oscillator interacts with the string, is just given by t times Wx here, where Wx is the jump discontinuity of the slope of the string. And the nice thing about this is it's a Hamiltonian system, and it's linear, and you can actually solve for W and reduce. And it turns out what you get is a reduced form of the dynamics, if you just look at the oscillator, that exactly has this term T here as the damping. So it's just the oscillator plus a damping term. And you can think of it as a kind of Rayleigh dissipation of the form that I looked at with Tudor and Jerry that arises in this infinite setting. And the nice thing about it is it's still Hamiltonian, but it gives rise to this dissipative dynamics. And if I have time at the end, I'll come back to how you can also do this in the non-holonomic setting. Yes, Darryl. You could, I guess. I hadn't thought about that. Yeah, so I don't know if that would be physical. I've actually never thought about that. I mean, so it wouldn't be this physical model, but I guess in principle you could do it. But yeah. But yeah, so the way you think of it is just energy going out. Anyway, that's the physical model. So one of the things that came up yesterday as a sort of prelude to this is how you might quantize a non-holonomic system. And in fact, this is related. This is partly why we originally thought of this. So for a non-holonomic system, as people discussed yesterday, one doesn't have a natural Poisson bracket. So it's not easy to see how to quantize it. But there is a way to quantize at least a couple of non-holonomic systems by thinking of them as infinite dimensional systems where you impose the constraint via a kind of field, which gives rise to this kind of damping. So I hope to get to that at the end. So now I'm going to transition to non-holonomic systems, and we'll look again at the kinds of Hamiltonian versus non-holonomic behavior that you can get in this setting. And I'll also relate it a bit to Toda and double bracket behavior, as I mentioned. Am I audible, by the way, still? Is this? Yeah. Okay. So this is a prototypical non-holonomic system, which doesn't behave in a dissipative way. So this is the vertical disk. It has the configuration space of R2 cross R1, S1 cross S1. So I'm just driving my disk around on the plane, and I can turn it and roll it around. So this is a sort of nice system to think about for various reasons. This is the Lagrangian for the system, the kinetic energy. And the non-holonomic constraints of rolling without slipping are just these two constraints over here. And you can write down the dynamics. So here it is. It's given by the Lagrange-D'Alembert equations. So basically, the forces of constraint impose constraints on the motion. These are velocity constraints. And it's also nice to think of it as a control system. One can put in controls U1 and U2. And U1 and U2, the natural controls, are controls on the turning and the rotation. So you can think of it, if you like, as driving a simple car. So this is a nice non-holonomic system, and you can see in the setting the nice sort of duality between controls and constraints. And the important thing about it is it's a Lagrange-D'Alembert system, but it's not a variational system. So this came up a little bit yesterday. Another way one could have done it, or the naive thing to do in some sense, is to just append the constraints to the Lagrangian. If you append the constraints to the Lagrangian, you get so-called variational non-holonomic mechanics, or vaconomic mechanics. And as was mentioned yesterday, so Jerry certainly didn't like the term vaconomic mechanics. The history of that's a little murky. I think it was coined by Arnold. So some people think it means, what is it? It's Kozlov, Arnold, Kozlov, and I've forgotten the first V. Vinogradov. Okay, Arnold Kozlov. That's not, I don't know if that's really where it comes from. But anyway, so Jerry didn't like vaconomic mechanics, so we always made sure to call it variational non-holonomic mechanics. But that's also a little bit weird because, of course, non-holonomic mechanics is not variational. In some sense, that's the whole point. Non-holonomic mechanics is non-variational in general. So anyway, the Lagrange-D'Alembert is the right approach. And the reason we know it's the right approach, well, there are two reasons. One is experimentally that turns out to be the right thing to do. If you look at systems, they behave like Lagrange-D'Alembert systems and not variational non-holonomic systems. And secondly, this is just Newton's law. So the right thing here is to use Newton's law. And Newton's law, apparently, is not always variational. So sometimes things are variational, sometimes they aren't. So here in any case, here is how you write down the equations of motion. So this goes back to this paper that I wrote with Jerry and Richard Murray and Krishna Prasad. But there's all this nice work, in particular this wonderful paper that Jair Koiller wrote in 1992, and other interesting work that you've seen discussed here by Tauler and Luis and Fedorov and so on. So here is a way to write the system so that I take the Lagrange-D'Alembert principle. I have constraints that in general look like this, mixing up the variables which I've called S and R. I have a Lagrangian, And the dynamics is given by this Lagrange-D'Alembert principle. So I take variations, integral a to b of L dt, and I choose variations, delta q of the curve, that satisfy these endpoint conditions and satisfy the constraints for each t. And the principle is supplemented by the condition that the curves satisfy the constraints. And the important thing here is that you take the variations before imposing the constraints. That is, we impose the constraints on the family of curves defining the variation. And this is the difference with the vaconomic mechanics. In the vaconomic mechanics, you're imposing constraints on the variation, on the curves. So you're restricting the class of curves. Here we're not. That's the key difference. And if you do that, you end up with this very nice set of equations. So there are various ways you can write them. I've written this in this reduced picture. The constrained reduced Lagrangian here is LC, where I've substituted the constraints into the Lagrangian. And again, that's okay if you do it after you've done the variational principle, but not before. And you end up with a system which looks like these Lagrange-Poincare equations that we saw yesterday due to Marsden and Koiller. They're various sort of gyroscopic type terms, and you saw this in Luis's talk, these terms CCAB, for example. And you can think of it as a sort of a set of Lagrangian equations and a set of Hamiltonian-like equations, which are correspond to the symmetries of the system. And this is basically the generalized momentum equation. And the important thing here for a non-holonomic system, again, is that Noether's theorem holds only in some sort of generalized sense. Sometimes if you have a symmetry of the system, it gives rise to a conservation law. Other times it gives rise to a dynamic equation, and that's the dynamic momentum equation, the so-called generalized Noether equation. So here are a couple of examples. There are lots of fun examples you can see, and Luis mentioned and Paula yesterday a number of fun examples you can think about. One of the simplest example, which sort of represents the dissipative behavior of non-holonomic systems as opposed to the Hamiltonian-like behavior which the disk represents, is the sleigh, the so-called Chaplygin sleigh. So here is the Chaplygin sleigh. It's just a tripod, if you like, so a three-legged stool with two legs, which are ordinary legs, and a third leg, which is a blade. And the important thing is that the center of mass is displaced from the contact point of the blade. If they coincide, then it behaves like a Hamiltonian system, very much like the disk. If they're separated, then you get all sorts of interesting dynamics. And in particular, it likes to go one way rather than another. It likes to sort of have the blade trailing the center of mass. And that gives rise to sort of asymptotic type behavior. And you can see this in a number of ways. The simplest way, if you like, is just to look at the equations of motion. And again, you can derive this the way I gave you, or you can use Newton's laws. So it's quadratic on the right-hand side, just like the general equations that I showed you. And you have a family of relative equilibria given by omega equal to 0. And linearizing about any one of the equilibria in the stable direction, you find a 0 eigenvalue and one negative eigenvalue. In the unstable direction, you get a positive eigenvalue. And basically, the solution curves are ellipses in the VW plane with a positive v-axis attracting all solutions. So the picture is this thing over here. So if you're on the omega axis over here, you get a little motion which takes you from the negative axis onto the positive axis. So it looks pretty much like the harmonic oscillator, except that the trajectories sort of meet in the middle there, which is something you wouldn't get for a standard Hamiltonian system. But as I mentioned here, actually, this is also in some sense equivalent to Toda. It meets Toda in a sort of interesting way. You can check that if you just take the lowest non-trivial Toda and you restrict this variable omega to always be positive, in fact, it does give you the Toda lattice. So it turns out that this is essentially like two copies of the Toda lattice. So there's this interesting little connection that arises for this system. And I'll come back to, as I said, double bracket type dynamics later on. So you can extend this to various other systems again, just like Toda. It generalizes quite naturally to Lie groups and Euler-Poincare type systems. We saw a little bit of this yesterday, but let me say a little bit more now. So the Euler-Poincare system, of which the Chaplygin sleigh is a special case, is like this. I have a Lagrangian, which is quadratic in angular velocities omega A and omega B. And I have some sort of left invariant constraint, for example, that looks like this. And you can have many constraints if you want. But the two classical examples are the one I just mentioned, the Chaplygin-Slay and the Suslov problem, which go back to Chaplygin 1895 and Suslov in 1902. So I mentioned the Chaplygin-Slay. The Suslov problem is also a rather wonderful problem. So this is basically just like the rigid body equations, this time on SA3, but where I have an interesting constraint. So I have the system I omega dot equals I omega cross omega, where I have a linear constraint on the velocities, which of course is a non-holonomic constraint since these are angular velocities and they're not integrals of any coordinates. So this is a non-holonomic constraint, even though it looks rather simple. You can write down the equations of motion just using that Lagrange-D'Alembert principle in the simplest possible way. And this turns out to be nicely solvable. You can solve for lambda. And it turns out, if you do that if A is an eigenvector of the moment of inertia tensor, then the flow is measure preserving. So that's the interesting difference. So for the Chaplygin-Slay, it's the point of contact being the same as the moment of at least the center of mass. Here it turns out to be this condition that distinguishes between dissipative dynamics and non-dissipative dynamics. And you can abstract this in a quite general way. If we just take the general Euler-Poincare-Suslov equations, or the general sort of equations that I wrote down earlier, I can write down the dynamics in a quite a general way. So the idea is the following. You want to consider which systems exhibit asymptotic behavior. Following Kozlov, and you saw some of this in Luis's talk yesterday, I first of all take the unconstrained equations, which are just given in this quadratic form. We know these well, say the rigid body type equations. And one considers when these equations have a natural invariant measure. And Kozlov, in this paper 1988, as Luis mentioned, showed that these Euler-Poincare equations have an invariant measure if and only if the group G is unimodular. And I think Luis mentioned that condition. The criterion for unimodularity is just this condition CCAC is equal to 0. And the definition is the group has a bilaterally invariant measure. And you can relate this, as Luis explained, to the Liouville theorem, I should say. The flow of a vector differential equation x dot equals f of x is volume preserving if and only if the gradient of f is equal to 0. And it really all follows from this. So if you just take that natural gradient condition, it gives you these nice conditions. And in particular, there's this theorem of Kozlov's that a flow due to a homogeneous vector field in Rn is measure preserving if and only if the flow preserves the standard volume in Rn. So that's a sort of very clean result. And in fact, nothing to do with constraints. It's quite a general result. Then you can sort of extend it to the constraint setting by just generalizing what we had before. You just throw in a Lagrange multiplier, and you can get this very nice generalized condition on whether or not the system has an invariant measure. So again, basically just coming from the divergence condition. And so this was proved by Kozlov for compact algebras, and I believe for Jovanovic for arbitrary algebras. And you can write it down in coordinates. And the nice thing is for a compact group, it reduces to this condition I to the minus 1 a comma a equals mu a. And for our 3x3 sort of Suslov type system, this reduces exactly to a being an eigenvalue of the moment of inertia tensor. So it reduces back to this nice physical thing. And the Suslov problem, as I guess some of you know, it has this nice, it's got this very nice interpretation, by the way. You can just think of it as a rigid body inside a sphere. And what you do is you just put a big rigid rod through the sphere, and there are two sort of blades that move inside the sphere, and that sort of restricts the motion. And where that sort of rod intersects the sphere determines what sort of dynamics you get. So a little artificial in a way, but nonetheless there is a physical version of it. And you can relate it to a skew-symmetric symmetry, actually. So you can say that the compact Euler-Poincare-Suslov system is measure-preserving if the constraint vectors are eigenvectors of the inertia tensor, or if the constraint system is Z2 symmetric about each principal axis. So in some sense, what you can see here is that measure preservation or volume preservation is related to discrete symmetries, which is sort of interesting. And again, you can see that if you look back at the Slay as well. And so you can generalize this in various ways, and particularly with Dmitry Zenkov, we generalize it to systems with internal degrees of freedom. So you can think of it, for example, as the Suslov problem with an oscillating mass inside it, or the Slay with a little mass vibrating back and forth. And you can generalize these conditions on measure preservation. So you can do this. And again, Luis mentioned he has examples where it generalizes to other systems as well, which I think includes these as a special case. So it's kind of fun to think about systems that behave like this. And the natural one that we thought of was this one, which is the Chaplagan sleigh with an oscillator. So this is work that I did with Jerry and Dimitri. So this is like a generalization of the Chaplagan sleigh, but this time, instead of the mass being fixed, it sort of oscillates back and forth about the contact point. And this is kind of a fun thing to think about. So you think it might sort of change from being measure-preserving to not measure-preserving, or what it's hard to know what actually happens, at least a priori for us. And we discussed this with Andy Ruino, who has pretty good insight on these things, but he wasn't sure about it either. Anyway, it turns out that it does behave like a Hamiltonian system. It's integrable. And in fact, you can show that the generic invariant manifolds are two-dimensional tori. So somehow the oscillation of this mass on the sleigh gives you a nice behavior. And here are some of these trajectories. So you get these rather nice spirographic trajectories. This is the trajectory of the base point of the sleigh. And it looks like spirograph patterns, if anyone here remembers the spirograph. And that's a great toy, which I believe is coming back into fashion. In any case, you just think of these two frequencies together. They're like Lissajous figures in a way. And you can generate all sorts of beautiful pictures. And it generalizes, in fact, to other systems if you connect it with a fluid and so on, like Luis has done. So that there are other things one can say about this. Okay, so those are sort of, so these are interesting systems. And it's amazing how rich these non-holonomic systems are. But in fact, the constraints, in fact, are linear. And of course, the dynamics is very nonlinear. So we were wondering a little bit about how one might generalize it to systems with non-holonomic constraints. There is some work on this due to Mal and others. And so what we started looking at a number of things, and this is sort of work in progress. But one of the things that we looked at was the thermostat, which is, again, a rather interesting physical system. So the thermostat is if you have a system in connection with a heat bath. So basically what you're doing is you have some sort of isolated system. You connect it to a heat bath, and it keeps the kinetic energy constant as opposed to the whole energy. And that really is a nonlinear constraint. So you can think of it as if you keep the energy constant, you're keeping V squared, for example, if all the masses are equal to constant, or sigma mi vi squared. And that actually turns out to be quite different from what happens in the non-holonomic setting, in at least the classical non-holonomic setting in some sense. So we go back to the non-holonomic equations. I have a bunch of constraints in the usual setting, and I have a bunch of forces. And the usual setting is this is a linear constraint of the form A of q dot. And the dynamic that I showed down earlier is essentially equivalent to this. And this is equivalent, as some of you know, to what's called the Gauss's principle of least constraint. So that's another way of getting it. So the Gauss's principle of least constraint basically says that the dynamics moves in such a way so that the system moves in the straightest possible sense, subject to the constraint. It's a local constraint. But it turns out to be this is what you really need to generalize it to the non-holonomic setting, at least to the non-linear non-holonomic setting. At least this is the ansatz. So you have to be a little bit careful about the kind of physics you get. But in any case, that's what we're using. It's that generalization. And in this particular setting that I'm going to talk about here, it's rather simple. In general, one has to worry about what happens when you have nonlinear constraints. In any case, so I want to say something about these nonlinear constraints now, related to particles, like the Toda lattice, and show you that you get some sort of similar dynamics in some sense. So here, again, we have n particles, just like the Toda lattice, with equal mass. All right, so the setting is identical. The only difference now is I have a constraint of kinetic energy being constant under the flow. So I'll write it like this. So V here is the velocities of the system. I have an n-dimensional force, F equals F1 through to Fn. And I'll have a constraint of kinetic energy imposed by some sort of, if you like, time-dependent viscosity, eta of t. So V dot is equal to F minus eta of t times V. And I'd like that eta of t to be such that I choose the system to have constant kinetic energy. So that's simple enough. So I want the norm of V to be constant, or V dot V is equal to 0. I can solve for eta, and I get this equation over here, which is rather simple, but it's a rather beautiful equation, actually. So F is some potential, and the nice thing is to think about it with different potentials. So in particular, you can look, for example, the case of a constant force. the simplest setting is n particles in one dimension subject to a constant gravitational force, F equals mg. So in the absence of the constraint, of course, the particles just move independently and the kinetic energy fluctuates. And we want to look at the case where they don't move independently, you have this constraint, and we want to see what the long-time behavior of the system is. So here it is, and you can do a kind of Fourier analysis to see what happens. So this is the dynamics of the nth particle. V squared is preserved by the dynamics. I define here this variable uq, which is sigma vn, e to the iqn. And q here is just 2 pi k over n. I define a quadratic mean velocity, and I just substitute back into the equations to get myself a nice set of equations of motion. And it turns out I get this set of equations. So u0 dot is equal to g times this quantity here. Uq dot is this general equation here. And it turns out that you can solve this absolutely explicitly, just like the total lattice, although I'm not sure if it's formally integrable in the same way. But there's a solution and long time limit just given by u0 of t equal to Vm tanh gt over Vm, which goes to Vm. And what that means, so the long time solution looks like this. Uq of t is equal to 0. And substituting back into my original variables, I see that the velocity of the nth particle goes to Vm. So in fact, what happens for this system is that at long times, the constraint enforces all particles to move with the same velocity in Vm. So I don't know if this is a priori obvious or not, but what happens is you start the system with arbitrary velocities. You impose the total energy, the total velocity is equal to, at least the total kinetic energy is constant, and all the particles move to the same energy. So you might wonder what the physics behind this is, and whether it's related to equipartition of energy. And I'll show you, interestingly enough, that it's not. So, so the potential energy is linearly decreasing. And I should say, by the way, one of the interesting things here is that the energy is not conserved. One of the interesting things about linear non-holonomic systems is that the energy is always conserved. So the volume may not be conserved, but the energy is. If you put a nonlinear constraint, it's not necessarily conserved. So now you can, for example, extend it to equipartition for particles of different mass. So I do the same sort of computation. The equations become a little more complicated. So this is the equation of motion for the nth particle. And again, I just write it down in terms of these mass modes. So I would basically do the same computation that I did earlier. And you can get a similar kind of dynamics. So this is the same sort of dynamics. So PQ of t evolves like this. It's some sort of quadratic equation. In the long time limit, you get this equation for PQT. And what you see is that in the long-term limit, Vn of t again goes to Vn. So surprisingly enough, even if the particle masses are different, at long time, the constraint again enforces all particles to move with the same velocity Vm. But this is not the same thing as equipartition of energy because they all have different masses. So the energy sort of is unevenly distributed among the particles. So that's sort of a curious result, but it breaks the equipartition theorem. So that's kind of a cute thing. Anyway, so what you can do other interesting computations. So there are various ways of generalizing this. You can take other constraints. You can take different forces, of course, and they all give rise to interesting kinds of dynamics. And you can also relate them in some interesting way to variational principles. So some recent work that we've been doing related to the kind of variational principles you get from nonlinear optics, at least from linear optics. And I'll hope to talk about that some other time, but I won't really say more about that today. But there is a kind of related variational principle, if you like, if you change the time. So you saw a little bit in Paola's talk yesterday about changing the time to Hamiltonize the system. So one of the things you can do a little with these systems as well is think about reparameterizing time. And in that case, you end up with a kind of interesting variational principle. But in any case, what I wanted to do here was related to these double bracket equations, what I started off with Toda. So let's start off for three particles. So here I have particles of equal mass. And because of the constant kinetic energy constraint, you can show that the particles rotate on a sphere. And this is actually the dynamics. So you get the dynamics as v dot equals omega cross v. And in particular, if you look at v1 dot with the force that's given to you externally, the equations of motion take this form. And you can write them in a rather nice double bracket form. So in fact, if you look at omega, the rotational velocity on the sphere, it's just 1 over v squared v cross f. So V dot is equal to 1 over V naught squared, V cross F, which this is that external force that I mentioned. And using the standard map that we all know very well from 3 vectors to matrices in SO3, you can rewrite this equation in this nice double bracket form. So this double bracket form, even though it appears to be rather special for Toda, in fact, pops up all over the place. And this is a very nice place where it pops up. So there it is. So the dynamics is in this double bracket form, which has this gradient-type behavior, but in this case reads to something rather different from Toda. Remember, at Toda, you sorted the velocities according to some sort of initial data. Here, the velocities are not sorted, but whatever initial data you take, the velocities sort of just equalize out, equal masses or not. So that's the thing. The n particle case turns out to be slightly different, so it's not quite double bracket in general, but let me show you what it looks like. It still has a very nice structure. So the dynamics in general is given by a skew matrix, V dot equals OV, where O is this matrix here, and the formal solution here is written in terms of a time ordering operator. And the equation looks like this if you write it in this form. So O is this rank 2 matrix, and again, rank 2 matrices are rather nice and pop up in integrable systems all over the place. But in any case, you can write down the system in this form over here, and if you just manipulate this function V dot F a little bit, you can check that the numerator of the system looks like this, and this function V dot F moves monotonically along the flow. You sort of get dynamics along a sort of n sphere that looks like that. And for constant forces, you can actually write this in a very nice explicit way. So if I just take constant forces, the equation of the nth particle again looks like this. You do a Fourier analysis of the type that I did before. And what you can show is, well, so this is a picture of the dynamics. And again, you can see it's the sort of, it looks almost like the Toda-like dynamics. This is the sort of sorting for the thermostat. The particles just move to these constant velocities. But again, during this kind of Fourier analysis, you can actually write it in a rather nice form, which is not the usual double bracket, but a kind of symmetric bracket. So if I take this constant force, the equation of motion you can write like this. It's V dot equals 1 over V naught squared, V tensor F minus F tensor V times V. That's that little rank 2 matrix coming in. Or if you rescale the time, you can write it like that. V dot equals this guy times LV. And if you consider the evolution of this operator L, which I defined here, so I defined the operator L to be V tensor F minus F tensor V, which is this little rank 2 operator. Then it takes this rather beautiful form. So if I compute L dot like this and use a little bit of your favorite vector identities, I can define a matrix B, which is analogous to the B coming in integrable systems. But in this case, the dynamics turns out to be written in an anti-commutator form. So it's actually L dot equals BL plus LB. So L dot equals B bracket L, which is actually not all that surprising. In fact, perhaps it's a little less surprising than the double bracket form, because a symmetric operator often naturally comes in with gradient-type systems rather than Hamiltonian-type systems. So it has this rather interesting form. It's a nice gradient flow, but certainly as far as I know, it's not Hamiltonian, at least witho't changing the time. Okay, so how am I doing on time, by the way? It's sort of 10 minutes maybe. Yeah, so I won't spend too much time. So I just want, so this is this, if you like, relates Toda back, at least relates Toda to the non-holonomic systems. Let me just say a word about how you might think about it in terms of the sort of radiation-type damping that I mentioned earlier. And this is it's related, in fact, to seeing non-holonomic systems as limits. And this is also a very nice thing. So one thing, of course, with a non-holonomic system, right, is you think of the constraint as being absolutely rigid, right? You cannot violate the constraint. But the particle, of course, in real life could slip. And you might think of the constraint as coming from the limit of some sort of dissipation. So if you have very strong dissipation, it'll make the constraint rigid. And there's a rather nice history of this going back, in fact, to Kara-Teodori, who wondered if you could, in fact, do exactly what I just said, get the non-holonomic constraints by the appropriate limit of a strong dissipative force. And the person who sort of worked this out in a good way, in fact, was Kozlov, who we already heard quite a bit about. So what he did was sort of add a parameter-dependent inertial term to the Lagrangian and showed that the unconstrained equations approach variational equations as the parameter approaches infinity. So that's the sort of Baconomic case. So Kozlov looked at the Baconomic case as a limit of the of highly dissipative systems, but it turns out to be closely related to the non-holonomic case as well. So, so as I said, you want to sort of view them in some sense as coming from infinite friction, and you can do this in the following way. So this, as I said, goes back to Kara-Teodori, who actually claimed that so Kara-Teodori actually worked on this, but claimed that it couldn't be done. So, but in fact it could be, and he actually had the right idea. If I've got the history right, Fourier showed that it was indeed possible, and the general case was considered by Kozlov together with a Vaconomic case in Karapetyan in 1983. And the idea here is to take a nonlinear Rayleigh dissipation type function that is actually just the square now of the constraints. So sigma a, j, q, I dot is the constraints. So you saw earlier for the Lam system a simple Rayleigh dissipation. This is a nonlinear dissipation. And the idea is just to take the limit of this thing as it goes off to infinity and to enforce the constraint rigidly. And using Tikhonov's theorem for singular perturbations, you can actually get the non-holonomic dynamics. And the idea, of course, in the setting is the system, though, is really not Hamiltonian because, you're imposing some sort of dissipation. And we wondered if you could keep it Hamiltonian. That's related to the Lam system that I'll mention briefly if I have a moment. So you can do this, for example, for the Chaplagan-Sley. And let me just show you briefly how that works. So the Chaplagan-Sley, which I showed you earlier, remember the tripod, just has this simple constraint. And you wonder if you can pose this constraint as the limit of dissipation. And in fact, you can. So here, again, are the constraints. Here are these equations. And now I just want to show you how you can get them as a special case where you also have some sort of dissipation. So here is the Lagrangian for the system, where the constraints enforced on the right-hand side. And what Kara-Teodori and Fourier did was simply add a viscous friction force to the Sley equations. So R is equal to minus nu, where u is the velocity perpendicular to the blade. So now what you're doing really is you're just allowing the blade to move perpendicular to itself, and you want to see if you can impose the constraint by letting an appropriate parameter go to infinity. And in fact, you can do that. So I said here, just changing variables, k squared equal to m over I plus ma squared. I put the parameter epsilon equal to this, and then you get these equations here, all right? And you can check that as epsilon goes to 0, one recovers the original equations. So basically, and it really is a singular perturbation theory. In fact, you get sort of fast motion onto the manifold where the non-holonomic system evolves. And actually, Kara-Teodori somehow missed this. He basically had the same setting, but he argued no matter how small the trajectory epsilon is, these equations yield trajectories which differ from the original system, and the dissipation could not yield the non-holonomic constraints. So somehow, in his original paper, which really is a great paper, he somehow missed that at the right point, but Fourier and company got this right. And if you just set here mu equal to epsilon a and sigma equals omega dot, you get these equations, and as mu goes to 0, you get rapid motion, except on this surface here, and that surface is the surface where the Sley moves. So it's all good, and you can recover it as a limit. So what we were wondering, and I'll just sort of end off with this very briefly, is whether you could actually keep it Hamiltonian. So there are various ways you can approach this, but one thing that we wondered is if you could do a sort of emulation of the Lam model, where you have some sort of field which imposes this constraint. And you can sort of do that, actually. So the question is, can the Sley motion be derived from a variational principle if you have the constraint coming from a field, and the field imposes this dissipative constraint? So that's what we did. So you choose a sort of appropriate free field. You couple this free field to the Sley with an appropriate form. And then what you can show is that in the limit, as the field becomes big enough, you actually impose the constraint. So this is the field equation. You take the free Lagrangian. So this, remember, is the Lagrangian for the Sley. But now I don't impose the constraint. I just have the free field Lagrangian and a coupling field. And I look at the dynamics of this thing as a sort of field theory. And what you can show, again, just using the same kind of argument as mu goes to infinity, and you use singular perturbation theory, what you get in the limit is the non-holonomic Sley constraint. So in that way, you've kind of enlarged it to a field theory, and you can make it still be a Hamiltonian system which sort of exhibits in the limit some sort of dissipative non-holonomic dynamics. And our motivation for this is something that came up yesterday. We wanted to see if you could quantize it. And at least in some cases, you can do this. So there is a way of quantizing this simple system. But the problem of quantizing non-holonomic systems in general remains sort of open. There are certain cases you can look at. But this is one case where it works. In any case, you can see again that there's this dual Hamiltonian dissipative non-holonomic picture, which comes out rather nicely in the sleigh is the prototypical example for doing that. Anyway, I think that's all I want to say. And again, thanks, Jair, for your inspiration over the years. And thank you again for the invitation to speak here.
Thank you very much, Tony.